Hi, everybody. Thank you for joining us in the Synthetic Intelligence Forum. My name is Vic, and I'm the founder and the host of the Synthetic Intelligence Forum. Today, it's my absolute pleasure to welcome Professor James Zou from Stanford University. Professor Zou is an assistant professor in the Department of Biomedical Data Science and has courtesy appointments in the Departments of Computer Science and Electrical Engineering at Stanford University. Thank you so much for joining us today, Professor Zou. I'm very excited to hear about this very interesting topic, data-centric AI, what it's good for and why do we need it. So the floor is yours. Please take us away.
Great. Well, thank you very much for inviting me. Excited to be here. So I'm excited to discuss with everyone around some of the recent advances in data-centric AI and why I think this is going to be really useful for a lot of the advances in machine learning. So my name is James Zou. I'm a professor at Stanford University. So just to set the stage and to motivate the rest of the presentation, so I want to first tell you a little bit about a detective story that we had to solve recently at Stanford. So here's what happened. So there's a lot of interest in developing and using AI algorithms for medical applications. For example, there's a lot of interest in using computer vision systems to detect skin cancer. How the algorithms work, that you take a photo of the skin lesion, and the algorithm, which will be running some convolutional neural network in the background, would then try to predict whether this is likely to be skin cancer or not. Right, so these kind of algorithms could be extremely useful because if you catch skin cancer early on, then you can sort of alert the patients and then save potentially a lot of lives. So at Stanford Hospital, they were interested in trying to deploy and test some of these algorithms. So we helped them to do a pilot study where we tested 3 of the state-of-the-art, these kind of algorithms for detecting skin cancer. What's interesting is that if you look at the original publications of these algorithms, right, they all had very good performance, right? The AUCs or accuracies would all be above 0.9 in the original studies. So then when we tested on the real Stanford patients, it was very surprising to us that the performance of all of these models on the real patients actually was quite poor, right? So the accuracy dropped to about 0.6 on the real patients. And just to be clear, there's no perturbations or no adversarial noises added to the data, right? So we just took the real images from the real patients. So the part of the detective story, the mystery, is to figure out, okay, so what actually happened, right? Why did these state-of-the-art models work so well before and works relatively poorly on the actual patients? So to solve that problem, we did a systematic audit of these 3 computer vision systems. And the goal of the audit is to basically to explain this gap, right? The gap of the original performance, the 0.93, to the actual test performance on the real patients, about 0.6. And we identified systematically several key factors that we think sort of mechanistically contributed and to explain why the models did so poorly on the actual patients. So the first big factor was that actually turns out that there's a lot of label mistakes in the original test data. So what actually happened was that the original data that was used to evaluate these algorithms, the original test sets, to generate the labels for that test set, right? So what they did was to have dermatologists visually inspect each of the images to say, is this a skin cancer or not skin cancer? Because that's relatively fast to collect. However, visual inspections by dermatologists also lead to a lot of mistakes, right? So the actual ground truth comes from you take a slice of the skin lesion and do a biopsy and do a pathology test. Right. So compared to that ground truth, there were a lot of mistakes in the original labels in the test set, which led to a substantial inflation of these models' performance. The second big factor was that there's a large data shift, or large distribution shift. Right. So the original data, training and test data, came from relatively common diseases because that's easy to collect. The patients at Stanford had both common and also less common diseases. So the models actually perform substantially worse on those less common diseases. So that also contributed to about 1/3 of the drop-off. So the third big factor, also really important, is that we discovered that these models, all of them, worked much worse on images that came from darker skinned patients. Right? So for example, if you look at the sensitivity of the models, the sensitivity here means that if the patient has skin cancer, how often would the model identify skin cancer, right? So that's really important. The sensitivity is actually really low, especially low when the model is applied to images that came from darker skinned patients. And when we try to dig deeper and understand why this happened, it turns out that the original training and test data sets for these models, they all had very few, in some cases, 0 images that came from darker or more diverse skin tones. Right. So I think this is an interesting example, case study that illustrates that if we really want to be sure that the models that we build and deploy in practice are reliable, oftentimes it's important to audit these models, and oftentimes the limitations of these models are revealed when we look at the limitations in their test or training data sets. And this is not a unique scenario just for that dermatology model. Right? So we actually, in a related work, we actually systematically analyzed many of the models that were approved by the FDA. Right? So over 130 FDA-approved AI algorithms. So these are algorithms that are approved by the FDA to be used on patients. Right? So each of the symbol here just corresponds to one of these algorithms, and I just stratified them by which body part they apply to. So we did a similar kind of audit to see what was the data that was used to train or to evaluate each of these FDA-approved medical AI systems. And I won't go into too much detail here, so the details are presented in this paper. But the main insight here is that actually most of these algorithms had similar kinds of limitations as we saw in the dermatology example. Right? So many of these algorithms have substantial limitations in their test and training data sets. So I think this problem, this challenge of the data is really prevalent in all areas of machine learning. So this really motivates why we're very interested in taking this data-centric perspective to help us to build more reliable and more trustworthy AI systems. So I want to explain a little bit about what we think is, what is this data-centric perspective and how this complements the current approach of machine learning, which is typically more model-centric. Right, so the most of the machine learning research is focused on improving models. Right, that's why we call it model-centric. If you look at most of the NeurIPS or ICML, ICLR papers, including many of the ones that we write, the typical papers would say, okay, so here's a standard benchmark data set. Right, there are many common data sets that are often used. And then the focus is that we assume the data set is fixed. The focus is already on how do we improve the models and the model architectures and optimizations to get better performance on these benchmark data sets. Right. So that's why we call it model-centric, because the focus is on the model, assuming the data is fixed. The complementary perspective, the one that we want to focus on today, is the data-centric perspective. Right. We oftentimes, there are more and more mature and standard ways of actually building models. Right. For example, you could use AutoML to help you train neural networks and optimize these different hyperparameters. So now we actually assume that we have a pretty standard way of building models for given data sets. And now the key question is, how do we systematically improve the data set itself? Right? So that when I feed this data set into my machine learning pipeline, the model building pipeline, then I get better and more reliable or more equitable performance downstream in deployment. Right? And here's just a simple experiment to illustrate why we think this data-centric perspective is quite important. Right? So the blue curve, the green curve here corresponds to the performance, right, of this pretty standard computer vision model if I train it on sort of denoised data set, right? If I put some efforts to denoise data set first, then here's how well the model will perform. The other three reddish curves all corresponds to training different architectures on this noisy data. Right, so you can see that there's some very relatively small amount of variations by trying to improve the model architecture on the noisy data. However, if I just denoise the data first, then I can actually see a really substantial improvement in the model's performance. Okay. So this is why we believe that even this data-centric perspective is relatively less common right now. Right, 99% of the research is focused on improving the models, but that's what we think that there's actually quite a lot of leverage, right, gains to be had in thinking about ways to improve the data sets itself for machine learning algorithms. So to help to set the agenda, right, for this emerging field of data-centric machine learning, data-centric AI, last year with a bunch of colleagues, we published sort of a paper that sort of lays out what we think is really kind of the exciting roadmap for data-centric AI. Right? And I want to break down this roadmap along the different steps, right? The different steps for how data comes into your machine learning pipeline. Right, so, and this is explained in more detail in this paper here. So the first step, right, is typically designing what data to use, right? So typically, if you are a machine learning engineer or practitioner, you have to figure out, okay, what are the data sources, right, and how to collect this data for building your application. So there's a bunch of questions around data sourcing, how to ensure your data has good coverage and good documentations. Right? So we've been doing a lot of work, right, on thinking about how do we make that more rigorous and more systematic. So for example, for this dermatology example, right, so now that we identified there are issues with the data in that there are oftentimes images from darker skinned patients are not present in the training and test data. In that case, we actually worked together with dermatologists to create a new data set that we call the diverse dermatology image data set, which is the first data set that actually has images from across different skin tones, right, to test and to benchmark these algorithms. So after you've designed what kinds of data you want to collect, and maybe you have started collecting those data, and then a big component, right, a big challenge for the next step is what we call sort of data sculpting. Right, so data sculpting involves things like, how do I figure out, now that I have maybe heterogeneous or potentially noisy data, right, how do we figure out what subset of my data maybe is the most useful and informative, right, for training my machine learning model? Or maybe my data has a lot of noise, as we saw before, right, label noise or feature noise, then how do we systematically denoise the data, right? Or make sure that the data is consistent across different umbrella that I'm calling data sculpting. How to sculpt your data sets to make it the most AI applications. And the third step, right, is now that after I have maybe trained my model on my sculpted data sets, there are a lot of really interesting questions related to what are the data strategies for testing and for evaluating the model, right? Because as we saw before with the dermatology case study, right, to test these models can be quite subtle and challenging. And here there's interesting questions around how do we maybe identify different subgroups of the data sets where the model is performing particularly poorly on those subgroups, right? So that's what I call the error discovery, right? You can also do different kind of data ablations when you do these model testing. So in my group, we've also been doing a lot of work on these kinds of data testing strategies. And one sort of overarching set of challenges that pervades throughout this pipeline is that there are lots of interesting and important data policies and requirements, right? Things like privacy or agency, right? So for example, in the European Union, in GDPR, right, there are stipulations that users can request to have their data being deleted, right, from a machine learning model. And how to do that for models like GPT or large language models is an open challenge. Right, so we've also been working on how do we efficiently make sure that our algorithms can be compliant with all of these data policies. So I think this is sort of an interesting roadmap, right? And there are a lot of interesting challenges here. So for today, I will just go through two specific examples, take a deeper dive into these two things that I highlighted in the red box. So the first part will be under this umbrella of data sculpting. We've been doing a lot of work on this problem that I call data valuation, right? So how do we figure out among all the data that you have, right, what's the subset of data that's the most useful? So I'll talk about that first and describe some approaches that we developed called data Shapley values for how to help us to do data valuation. And the second part I'll describe is on this third component for data testing, right? In particular, I'll talk about different interesting ways to leverage large language models or visual language models to do automatic error discoveries for different subgroups of my data. Okay, so diving in first into data valuation. So here's basically the setup, right, for a data valuation problem. So typically in machine learning applications, right, so you have some training data that can come from different individuals or different data vendors or different sources, right? It could be from different hospitals, etc. And for your training data, given the training data, then you have your favorite learning algorithms, which could be your favorite neural networks or something simpler like random forest or SVM, right? And by training this algorithm on your training data, your model achieves some level of performance, right? You can pick your favorite performance metric like F1 score or accuracy or some other metrics in deployment. Now, once my model achieves some level of performance, right, maybe achieves like 80% accuracy, right? Ideally, I would like to be able to attribute or partition that 80% accuracy back to my individual training data, right? I would like to be able to say that, oh, data from this kind of training data is responsible for 50% of these correct answers, and these other training data are responsible for less, right? And similarly, if my model exhibits mistakes or makes mistakes or exhibit certain biases in practice in deployment, ideally, I would also like to be able to attribute that back to the training data and say, oh, it's this kinds of data that perhaps introduced noise or spurious correlations into my model that are responsible for these kinds of mistakes and biases. Right. So because if I can then attribute the model's performance at the very end back to the original training data, right, to specific kinds of training data, then the whole system is much easier to debug and much more transparent and easier to improve. Right. So, and I think this data valuation is really useful, right, for different stakeholders in the machine learning system, right? So if you are a machine learning engineer and practitioner, oftentimes, like a lot of your time is spent on figuring out what kinds of data to use, right, or what kind of data to collect. So the data valuation then would be a systematic, rigorous way to tell you, okay, here are the kinds of data that are the most useful for your machine learning model, for your specific model, right? If you are oftentimes, there are also these data vendors, right? There's people who are collecting these data sets and to sell these data sets to practitioners. Data valuation could also be a way to provide some guidance on how to set price for different qualities of data. So how do we then solve this problem of data valuation, right? So the first approach that people have often used and explored in the past is to do some sort of leave one out validation, right? Evaluation. So the idea here is quite intuitive, right? So suppose I have these three, in my toy example, let's say I have these three data sources. So each of these could be data from one hospital or from one user, right? And if I want to figure out what is the value, the contribution of this star data point, right? Then what I can do is I can train a model on all of my data, right? And this is just illustrating the decision boundary of my model. And then I can remove this point star and retrain my model and see how much does my decision boundary change if that data point is not present in the training set, right? And by measuring the model's performance due to that change in the decision boundary, that gives me some sense of how useful and what is the value of this point. So even though this is quite widely used, this is a big challenge of this is that it's actually very noisy when you have large data sets. Right? So in modern machine learning, oftentimes you're working with data sets on the orders of hundreds of thousands, maybe millions of data points, millions of images or text, right? So the impact of removing a particular point, right, from that million-size data set is going to be very negligible, especially considering there are other sorts of randomness that come from the random seeds in your optimization algorithms, for example. Right, so in practice, people are finding that these kind of leave one out valuation and just being too noisy to be useful on large data sets. So this motivates us to develop new ideas, new algorithms to help us to do data valuation that are more robust and more informative. So this is what I call data Shapley value. So it's also quite intuitive, right? So instead of doing this leave one out once, I'm going to do it a bunch of different times in parallel. So each time I do it, I'm going to look at a different random subset of my data, right? And in that subset of my data, right, here I'm showing you sort of three different random subset of my training data that I start off with. And in that random subset, I can then do this leave one out and see what is the impact of removing this point star, right? How that affects the model's performance when the model is trained on that subset. And the reason why this is helpful is that this gave us a bunch of different scenarios to estimate, right, the impact of this point star, right, in each of those scenarios, where each scenario then corresponds to a different subset of my data, so which approximates to different distributions. And in the end, we're going to basically average the contributions of this point star across these different scenarios into one value, right, one score for that point. That's what I call the data Shapley value. Right? And by doing this across these different scenarios, then I'm getting first, much more robust estimate of the value of this point. And then second, it also helps us to disentangle the potential interactions between different data points. So this is just writing out in mathematical formula what I just described in the picture, right? So the value of a data point k, right? It's just going to be an average, a weighted average of the marginal contributions to adding this point k to different random subsets of my data, right? So the S here would indicate different random subsets of my data, and we're going to see how much this model's performance that's trained on S improve if I add this data point k to that subset. Right, so this has a lot of really nice mathematical properties. And so first, I just want to tell you about some of the applications of this data Shapley value, right? And then come back toward the end on how do we compute this efficiently. So one application is that we can use this data Shapley value to help us to identify which data points are mislabeled, misannotated, right? Which, as we saw in the beginning example, that's a common challenge in real-world data sets. So what happens is that we actually apply data Shapley value to these large medical image data sets, including these kind of large X-ray data sets. And when you apply data Shapley value, one interesting thing happens is that a bunch of data points seems to have negative values. Right? So a negative Shapley value would suggest that those data points are somehow hurting the model's performance. And then what we did is that we took the data points that have these negative Shapley values, and we had a panel of radiologists, right, to systematically re-examine each of those data points, each of those images. And remarkably, in 60% of the time, those data points that have low or negative Shapley values were misannotated in the original database. Right? So the original medical records, maybe it was annotated that this patient had pneumonia, but when we had our panel of 3 to 5 expert radiologists re-examine that image, they decided, oh, maybe this is ambiguous, but the patient didn't have pneumonia. And by looking at the data points that have negative Shapley values, this was actually very effective in identifying mislabeled data sets, subsets of data that are mislabeled in my training data. And by removing these data points that have low Shapley values, that's this blue curve here, then I can see that my model's performance really can improve quite substantially. So a second example is that I can also improve my model by using this data Shapley values to data averaging, data weighting. Right. So in the dermatology examples we saw before, the training data can also be very noisy, heterogeneous. And that's why if I take my models trained on this noisy data and apply it to the real patients, right, the accuracy drop off quite a lot. And the data Shapley value then will compute a score for each of these images. Right. The score, if it's positive, suggests that this image is more informative or higher quality and helps the model to do well. If it's a negative, then this means that the images are either mislabeled or contains various correlations or noise or just not informative. And then the natural thing to do is I can just take our model, the same architecture, and then retrain the model on the data that's weighted by the Shapley scores. Right? So this is sort of naturally encourage the model to pay more attention to data points that we believe are higher quality or more informative or have better labels. By doing this, we can actually already see quite substantial improvements in the model's performance in deployment, where the accuracy can improve by over 10%. The third example is that this data Shapley value can also help to improve the fairness of these models. Right. So one challenge with a lot of these computer vision systems is that, for example, if you train them on the training data, often the training data are a lot of demographic groups that are underrepresented in the training data, so that when you take this model and deploy it in practice, right, often the performance could be worse and drop off for these underrepresented minority groups. In this case, right, the data Shapley value also computes a score that says like how important is this particular training data towards how well the model performs for these underrepresented groups in practice. And by doing a similar idea of weighting the training data by these Shapley scores and just retraining the model on the weighted training data set, we can also improve the model's performance across the board, but especially for the minority groups. Right? So this improves the fairness of the model in applications. And the nice thing about this kind of a simple approach about reweighting the training data by the Shapley values is that you didn't have to go out and collect additional new data, right? So the data is already there. You're just helping the model to take better advantage of more useful and higher quality data. So hopefully these three applications gives you a sense, right, of how you can use data Shapley values in your work in practice. So to compute the data Shapley values can be challenging. So a lot of the work that we've been doing in my group and also with work by our colleagues is on coming up with efficient algorithms for computing data Shapley scores. Right. So I won't go into this in too much detail, but there are basically two types of strategies that we have been developing for quickly estimating data Shapley values for very large data sets on the orders of hundreds of thousands or millions of data points. So one type of strategy is that you can actually, turns out that for specific machine learning models, we can actually derive analytic mathematical formulas for data Shapley values, right? So these are analytic formulas that we can then just plug in the data and then get the value out immediately. So these are very fast. So these are working for relatively restricted classes of machine learning models so far. But one thing we can do is to basically take some sort of encoders of my data, right, and assume that's fixed, and then compute data Shapley values on top of the representations from those encoders. Right, so that's would be a very, very efficient way to leverage these analytic formulas. And in general, right, for general machine learning models, another approach is to basically do Monte Carlo estimations. Essentially, we can sample different random subsets to estimate the data Shapley values. So that's also quite practical in applications. And oftentimes, the Monte Carlo will converge very quickly. Right? So we have some algorithms and theory to demonstrate this. With these kind of approaches, for example, if you have your neural networks, you can sort of scale, be able to compute data Shapley values quite efficiently on neural networks trained on data sets of hundreds of thousands of images. Okay, so that's the first part about data valuation. And in this last 10, 15 minutes, I want to tell you about sort of the second part, right? The second example, where we can take a deeper dive in how to do more fine-grained error analysis for machine learning. So why do we want to do more fine-grained error analysis? So the motivation here is that oftentimes, right, people look at standard machine learning metrics, which are just measures aggregate performance of a model on a test set. Right? Maybe I've looked at the aggregate AUC, the aggregate F1 scores, right, on my test sets. And in many cases, as we saw with the dermatology example in the beginning, right, the aggregate performance by model on a data set can be very misleading. Right. The model could do well in aggregate, but still have critical limitations on important subgroups, which, for example, like the subgroup of patients that have darker skin tones. Right. And by doing this fine-grained error analysis, the goal is to go beyond the aggregate performance, but to identify what are the performance of the model on important different subgroups that can give us much more direct insights on how well my model is working, and also on how to improve my model efficiently. So then how do we do this more fine-grained error analysis, right? So if we have structured metadata, like if I know for each of these training data, like what is the age or the user type, right, then I can simply stratify my model's performance by that metadata, and that's relatively straightforward to do. However, when we're looking at unstructured data, where we don't have the metadata, right, maybe I have just unstructured images and text, where I don't have these additional annotations, then that becomes much more challenging, right? So a lot of my research in my group is to focus on how do we do these kind of fine-grained error analysis in a systematic way when we have unstructured data. And our approach is to basically leverage a lot of the recent advances in language models and visual language models to essentially help us to automatically summarize mistakes, right? So the strategy is sort of a two-step strategy. The first is we want to first identify among all of my data sets, right, identify semantically meaningful clusters of mistakes. Right, so are there particular clusters of my images or text where the model is making a lot more mistakes than we expect by chance? Once we identify those clusters, then we're going to use large language models or visual language models like CLIP to help us to automatically summarize, like what's common about those mistakes. Right? So then this can give us mechanistic insights into what's leading the model astray. So I want to illustrate this through both applications in computer vision and also applications in language models, natural language processing. So in computer vision, right, so here's how we sort of implement that two-step strategy. And the details are described in this iClear paper last year. So the first step is that we're going to take a computer vision model, maybe that's trained on a bunch of large image data sets, right, and evaluate it on a large image data set. We're going to cluster first, right, the image data set into different semantically meaningful clusters. And we can do this by leveraging this representation space for models like CLIP, right, that has sort of more semantic understandings of the different image encoders. And we have a particular clustering algorithm that we developed that can especially pick out clusters where there's a lot of more mistakes, right? So here's a cluster of data where the model seems to make a lot of mistakes. And then we're going to use language models to basically help us to explain what is common about those mistakes that led to the classifier, the predictor astray, right? So in this case, where we use models like CLIP that has both the visual encoder and also this language understanding to help us to explain these mistakes. Right, in these particular applications, right, so here are just some examples of the mistake clusters that are identified by our clustering algorithm. Right, so these are basically images where my original image recognition system seems to be making a lot of mistakes. And then these are basically fed into the explainer module, which is using CLIP. In this case, it basically explains that, what's common across these mistakes is that they seem to be mostly looking at the interiors of cars. And it turns out that the original classifier was doing quite a poor job. It's not able to recognize cars when the photos are taken from the interior of the car. The second cluster of mistakes seems to be basically a lot of cars in raceways, right? That also identifies a limitation of the model, whereby it's making a lot more mistakes in identifying cars when the cars are in this racetracks. And we have also implemented a similar kind of strategy for analyzing text data, right? So the idea here will follow the same kind of meta strategy where we first cluster the text data in a way that's semantically meaningful, right? And then we use leverage different NLP models and language models and topic models to help us to explain, okay, what is common about each of these mistake clusters? So this is implemented into an interface on Hugging Face, right, where we can actually do this interactive visualizations to look at for what are the mistake clusters. In this particular case, this is for a sentiment analysis application, right? When we take basically a model that's doing these sort of sentiment classifiers, and we identify that there are several clusters of data where this kind of sentiment classifier is just making a lot more mistakes. And one of those clusters basically corresponds to, it seems like chain restaurants, right? So it seems like there's a particular way that people describe chain restaurants that led these models to make more mistakes. Right? So that also gives us useful insights. And the last part I want to mention is that now that we identify clusters where the models can make mistakes and are making more mistakes by chance than we would expect, it would be very useful to be able to come up with like a mechanistic explanation for why did the model make a particular mistake. Right? So let's say if the model misclassified this image to be crocodiles instead of zebra, right? We'd like to understand like, what really are the mechanistic information that led the model to make that mistake. In this particular case, right? So we developed a system that we call natural language explanations of mistakes. I'll describe how that works in a bit. But in this particular application, we are able to explain that, the reason why this model made this mistake is because there's too much water in the image. Right? Essentially, the presence of water is what led the model astray, right? To let it to predict crocodile instead of zebra. And if there was less water in the image, then the model would have actually correctly predicted this to be zebra. So here is how this conceptual explanations of mistakes work. It's described in detail in this ICML paper from last year. The high-level idea is that the goal here is to basically provide high-level conceptual explanations for individual mistakes that the models make. Right? And we're going to do this by essentially combining, right, concept-based explanations, right, with counterfactuals, and to generate sort of counterfactual explanations. So here's how this works. Right? So because we want to provide these more high-level explanations of these mistakes, we're going to explain those mistakes in terms of concepts that are easy for humans to understand. Right? So concepts would be things like stripes, or water, or outdoor. Right? Each of those concepts will correspond to a particular direction in the embedding space of our models, right? So we can actually automatically learn those concepts, learn what we call a concept bank. So that's very easy to do. And once we've learned this concept bank, then we're going to perform this counterfactual analysis. The idea here is that basically you have an image where the model is making a mistake, right? And can I try to move it in some direction that's aligned with some of the concepts that we have, so that if I move this a little bit in that conceptual direction, then the model would have actually gotten the correct prediction, right? So this is actually done systematically through solving this optimization problem, where the details of the math are not so important, but the high-level idea here is that when we look at the original data, right, that's this term here where the model is making a mistake, we're going to basically look for a subset of the concepts such that if I move this data point in the directions of those concepts, right, if I add or subtract some of those concepts, then the model would actually have made the correct prediction instead of the wrong prediction. And then putting all of these pieces together, right, this is how we end up with explaining each of the individual mistakes the model will make. Okay. So here's an application of this conceptual explanation of mistakes, applying them to the real data sets. Right? So in this case, going back to our running example of the dermatology. So each of these 4 photos are examples where these dermatology models would make mistakes, right? So they would predict an incorrect label, incorrect disease. So that's what the prediction here is in orange, and the actual correct label is written in blue. And in each of these cases, our system is able to explain why did this model make that mistake, right? So in the first example, it actually turns out that the skin tone, the darker skin tone, is the mechanistic reason why this model made an incorrect prediction. So in other words, right, if the skin tone, because it had been less dark, right, then the model would actually have gotten the correct prediction on top here. In the second example, we identified that the blur of the image is the key mechanistic reason behind the mistake. Right? And if the image had been less blurry, then the model would actually have predicted exactly the right label, the right disease. In the third example, it turns out that the image is too zoomed out, right? So that's what led to the mistake. And the fourth example is because there's too much hair in the image, right? So the model was basically confused by the hair. So in each of these cases, by providing this conceptual explanation of mistake, we can then identify mechanistically, like what are some of the limitations of my skin disease prediction algorithm. And it's very useful in helping us to audit the model and also to help us to improve the model going forward. So just to summarize, right? So hopefully this demonstrates to you that I think why data-centric AI is really critical for helping us to build efficient and reliable machine learning algorithms and to deploy these algorithms, right? And here we think about, we can use data valuation as a set of approaches to help us to systematically study our data set, especially to identify which subset of my data is noisy and which subset is highly informative. And we can also use this fine-grained error analysis to give us mechanistic understandings of what are the model's weaknesses in this, for a specific subset of my data. Right. And these are just two basically bullet points under this broader data-centric AI umbrella. So a lot of the research in my group is also working on these other bullet points that I think are also extremely important and critical. So just to wrap up here, right? So all of the papers and the codes and the data sets that I mentioned in this presentation are available on my website. Here again are the different references for each of these works that I mentioned. And I want to acknowledge again all of the students and postdocs in my group that led these new algorithms and developments. So thank you very much. I'll stop here. Happy to have a question and answer discussion.
Thank you, Professor Zou, for a very illuminating talk. It was fascinating and great to hear that there are so many other areas that we could possibly dive deep into. So we'd love to have you come back and talk to us a lot more about these topics, but also the other topics. If I may, I have two questions. One from the first deep dive you covered around data valuation, and the second one around fine-grained error analysis. So the setup for my first question is it's very interesting how you talked about data valuation, because I remember from sort of more traditional uses of Shapley values to do model explanation explanations, essentially we build coalitions of features, and then by excluding certain features in each training run, we can essentially attribute back to each feature what its contribution is to the model. Here you're actually doing that more from a sample or an observation level. So that's fascinating. So my question is then, by extension, could we not take another approach such as permuted feature importance, where we're taking features one by one and then permuting their values and seeing what the impact is on the model's performance or the degradation in its quality? Could we take that kind of a permuted, not feature importance, but a permuted data or sample importance approach to do something similar to calculate another way of data valuation?
Yes, that's a great question and great observation. So you're absolutely right. So I think the data Shapley scores that we're developing here, we can view this in some sense sort of like a transpose of the feature Shapley values. Right? So instead of looking at the feature importance, which are typically like the columns, right? We're looking at the data importance, which are the rows, right? There are several sort of technical differences in how do we really estimate the data Shapley values compared to the feature Shapley values. It actually turns out that in some of these cases, it's actually easier to compute the data importance than to compute the feature importance. Right? So that's how we are able to scale this up very efficiently to large data sets. But I think it is a really interesting idea, like you mentioned, of leveraging these kinds of ideas of how to do permutations of data to estimate data values. Right. So in some sense, right, data Shapley value is one particular way to do data permutation, right? It's creating different random subsets of my data and then leaving out individual data points. We've also been exploring alternatives to the Shapley value. I didn't mention this here, but it's a very active area of research recently. So for example, we've developed this idea that I'm calling sort of beta Shapley values, which is like a different approach to do data permutation, also with the same goal of trying to compute a value for each data point. And there are many cases where the beta Shapley value is actually more informative and more gives basically more signals compared to the standard Shapley values.
Very interesting. Thank you. And we'd love to talk to you about that too. Professor, if I may, to the next question, which has to do with the fine-grained error analysis deep dive that you did. So one question that I had in my mind, it was fascinating that when you're trying to attribute sort of the causes of the mistakes, when there's mislabeled images, for instance, and you talked about sort of semantically related clusters causing mistakes. I suppose one question that comes to mind is, when we have images which are simple object detection, so you have one label per image, or even if it's multi-target and you've got multiple labels per image, could we extend this forward and take this to the level of actually semantic segmentation or instance segmentation, where we have polygons associated with objects? And so if those are wrong, can we then do a finer grained and even deeper analysis if we had access to that kind of analytic techniques applied to polygons and semantic and instance segmentation?
Yeah, that's a great question and a really interesting idea, right? So even when we look at object detection algorithms, let's say I'm trying to predict cats and dogs, right, with simple labels. There, what we find is that, like, what are the interesting semantic clusters, right? So there are clusters where maybe if I have cats that are playing in the yard, right, that's where the model makes more mistakes, right? So it's these additional information of that cluster of cats. Right? Maybe the model is doing well when the cats are indoors, but it's doing poorly when the cats are specifically playing in the backyard, right? So then ideally we want our semantic algorithm to basically cluster to identify, oh, here's a cluster of images of cats that play in the yard. That's where the model is making a lot more mistakes than everywhere else, right? And in order to identify that, it's also very useful for the model to be able to capture, like, okay, so what is it about the features of the yard, right? Maybe there are benches or there are fences in the background, right? And that's where I think some of these ideas about doing more semantic segmentation is also quite useful. Yes, this gives us more mechanistic insights into, like, what are the attributes, right, of that subgroup of mistakes. In some ways, that's what like the CLIP model that we're using provides some level of that semantic segmentation, right? Because it's able to have some understanding of, like, what are the objects in the background and what are the objects in the foreground. But I think that's a great area to explore further.
Okay, thank you for that, Professor Zou. And as you mentioned, there's so much more to cover in each of these topics, but also the broader umbrella that you kindly shared with us. So on behalf of the Synthetic Intelligence Forum, I'd like to thank you very much for this inspiring talk, but would love to invite you back so you can continue to share your knowledge and wisdom with our community. So thank you so much for joining us today.
Thank you for having me.